Okay, so hey, train your plants every day. Jordan Scoville coming at you from the STEM Lab. Number two for the Trainer's Manifesto, or the Trainer's Guide for the Bluestone Mill. So you got to remember, this is scale. This is scale and dimensions. And no matter what you do in the real world, it's got to be made up of some scale. You got to reference what an inch is relative to. Is an inch relative to a mile? Is the scale of the floor relative in scale to a lot of other processes and jobs that you might do? The question becomes, can any task be broken down using scales of these dimensions? And to know STEM is to have a very apt ability to adapt in that form on the fly. Um, the goal is not just to have a useful tool there to benefit yourself, but also to have an ability so it helps somebody else as well. Because a lot of things in this dynamic that we use nowadays is going to correlate to having multiple effects, and that you can capitalize and easily recognize that they have those effects. And that's to say you've engineered something that is highly useful, essentially. The more useful it is, the more practical it's going to be. The more useful it is, the more benefits you get out of it, and it's just going to feel more than some piece of paper, right? The idea is you can engineer what information is on a piece of paper that is useful across the board. And I'm not going to say everybody's going to recognize some trainer's manifesto as a STEM diagram. You know, kid in the shop, first day, probably very overwhelmed just by the raw information onto it, and probably very unaware of how high end complex the mathematics behind some of that is. So that's why I'm going to make this second video for it, because the reality behind that is I'm using all of the STEM problems to recognize this manual. And I've done it several times before. Sometimes I do it in raw mathematics. I actually apply the STEM mechanics themselves in talking about mathematics. But here's just another version of it that is a little bit more practical, but you won't recognize the STEM problems themselves. Erodes, an abruptly long sequence of reciprocating terms with differences, essentially. That's shorthand from the STEM problem that's worth like $5,000. Take any value. This is thermaling rock. That is a term which has not just an abruptly long sequence, number of points that makes that thing real, but also in the given name itself. Thermaling. Thermaling is torching. And to define it, it's going to take an abruptly long sequence. That's the idea. That's a dimension. That is a scale to a certain degree. Okay, Mason's degrees. Yeah, anyways, I like to have fun with it. It's the gravity under the mountain, man, when you got it on your shoulders. Anyways, what is Beals? Beals is stated, or excuse me, we'll start with Fermat's. Fermat's is this idea: it's an AX plus BX equals CX process. Well, in definition, while describing what thermaling is, or making pattern cuts, we're going to switch it up here a little bit. What is the difference, A, thermaling, against cutting pattern? One is AX, the other is BX. If integrated, you could see how they are equal. C, causally, this X dimension. Well, integrating that even farther, that you could say that both in a note breakdown, well, there might be an abruptly long sequence to it with differences in terms, are a AX BY CZ system. In many cases, they're not always linear to say, oh, I'm always going to thermal first. Sometimes I thermal after I process. Sometimes I have to flip and burn. Sometimes I have to do edges and things along those lines. And the processes in that form as much as individually to thermaling itself. That thermaling is an abruptly long sequence of terms. It has an AX BX process. It has a front line, a front dimension, it starts and it finishes. But to the idea that there is a process inside of that is thermaling, that is essentially completely different as much as identical in the form and scales and dimensions and timelines it may take. That's an AXBYCZ system. And that's Beals. Fremont's AXBX, Beals AXBY. And especially using things, this is something that machinists, where you have to kind of know CNC machines, saws, where you have X, Y, Z, W dimensions to take in consideration the raw form, becomes a really useful, practical thing that you can really see handy. You know, the idea is it's this movement. X is Y, and you're going to say, well, X is up and down. Y is left and right, but it's still 0, -1, +1. And the choice says sometimes I want to choose -1 and make the flip into a positive system. That's what I want it to do. That's in the same way this AXBY system with a Y dimensional application, or a W application. You know, that is the degree, you know, to the choices you make. And then forward and back still apply to the same model. You know, you're just taking fourth dimensional, fifth dimensional calculations from general relativity, and you're saying, well, this is the spectrum game. This is light here, you know, and how you define the X-rays that you might need to see through this process. That's just a fun way I like to quote it. So other things you'll need to know from the STEM problems is there's air turbulence equations, you know, and we're going to take this real simple, right? You know, this is meteorology, watching the hurricane to generally track where it's going to go, because there's a high pressure system over here, a low pressure system over here. If you can integrate those mathematics, it's going to get stronger, it's going to get weaker, it's going to course to the left, it's going to course to the right. And if you can say hurricane is thermaling, and you could say that's where I am in a real day from this general relativity, this one on the floor, looking around, I'm a warm-bodied Murphy. And this Murphyverse, and scale, grids, and everything like that, once you've taken your feet off the paper, if that makes sense to you, that basically what you're still doing is an air turbulence equation. And it gets into very complicated mathematics. You got the sum symbol, you got the environment symbol, you got the Planck fucking symbol, you got gradients, Lapicants, you got all those numbers thrown at you. And just here in the real world, those numbers correlate to grid, field, dimensions, particles. Particle is an air particle, isn't it? So a point, thermaling in the process of things, is a particle. It's an air particle. And you have to be able to adapt to the system under that idea. Mining a Bitcoin was one back in the day. Well, it has to do a lot of processing and mining for information. I have parts in front of me. I have built this automatic little machine here that in the computer universe says it's going to process information automatically to me. When I have certain things set up and I'm aware of what those really were once they were engineered, the result is this mining of information that says what I get out of this is information. And it's going to be built in that same form. This is not a multiple process. These are all individual things that you're looking at. And as you're looking at this grand total of all this information, it seems like all of those things play in sequence. And to a certain degree, yes, they do. In many and all cases, they do. But they're also, in their entirety, a definition of each individual STEM problem. Think about what kind of complexity it would kind of really take to understand some questions in mathematics that have $1 million values behind them. What would it really need to look like? How would it behave? What are some of the notations and actions that would make it what it is? So you would want something that has an effect. You would want an answer that in parallel has those same abilities. What other STEM problems are there? Yang-Mills mass gap. Well, determining what atomic mass is. Well, that's where you're going to get. The atomic weight of hydrogen is obviously 1. Yes. That's an element. It's a particle. So that's what we're going to take the definition of AX, BY, and we're going to discern the complexity of something in physics. Says it has nothing to do with this trebuchet shooting this giant rock to determine the mass and the forces that go into this. But here, the idea in quantum mechanics of taking processes under these ideas and saying, even though they have internal masses 0, they still have an effect of how they hit hypothetical walls on grid while designing them, that they still have as much mass as a 100 kiloton bomb when it goes off, when you think about the radiation or the fallout of not knowing those calculations. If you can by saying, hey, the mass gap it takes to train somebody or train myself, using those things to be aware of those ideas, those things, those points, those dimensions, those processes, those skills that essentially have no mass whatsoever, but while your feet are on the floor, have enough mass to concern what gravity is in the shop. They have pressures, they have timelines, they have very specific values in a world where otherwise it's no value whatsoever. That you could take the value of thermaling and use it in a resume to another job that doesn't thermal whatsoever, but still have an effect, like having value. That's the mass gap problem. The NP problem, the P versus NP problem, and now this is game theory, essentially. Well, it's at least a great way to describe it. All right, game theory is, especially in the NP problem, it's this idea that you have a chessboard. You're in play, 20 moves on both sides. I move 20 times, you move 20 times. Now the computer, the grid, the manual that you've made, has to be able to discern what the next move is most based on what pieces are left, what's locked in, what's not locked in. Obviously, the pawn that's locked in, that one can't move. But there's a pawn. There's another pawn over. There's 3 pawns on your side. You have a knight that you can move. The queen's still good. The bishop can move, and all those things can move. What is the best move? I don't know what the other person might play next. So to make that choice, it's essentially impossible to distinguish what the real best next optimal move will be. That's what the NP problem has. They want to build a computer that makes that choice for them, and that can be done. It was done with Blue and the world chess player in the world, and the same idea is the guy beat him. Even if the computer would have won, it could have been a failure in the strategy of a game, and it can really change. The engineering and designing of a model like that, when I talked in my last video about the optimal efficiency to design a thing, says, think about the number of pages that you might have to use. Using a computer is easy. You can slip it out for any given process. I'm going to take this chapter and slip it here because this is the next move they're going to make. I know that. I just want them to read linearly. The reality behind that problem is when you're into the place and you don't know, well, this is thermaling. Now I got to figure out where rock facing goes into the job. And just the number of processes of training them to idiot-proof a saw where pattern slips into it while designing that manual is the same thing as the NP problem. The design frame of that works discerns what that NP problem really looks like. And it's a great tool to describe the total faculties behind what it really takes to understand STEM problems, how to use them efficiently. So there's a lot more to it, but I'll catch you on the next one.